Yeah, so uh, good evening, everyone. And thanks, Faisal, for the nice introduction. And these days, you might have heard a lot about artificial intelligence, and alongside, you might have also heard about deep learning and computer vision. So today, I'll just brief through what is basic deep learning, computer vision. I don't go into much detail. Maybe after the presentation, we can have discussion if you need any extra information. So let me start with one example. This is a example for autonomous driving, where a driverless car is going to a busy street and it needs to navigate through the. How will you do that? There are like a lot of sensors associated with this. It's like lidar, radar, and camera is one of the sensor which can accurately perceive all the outside world and convert it into a digital. Then we can do the processing. Based on that, we can do the decision, like it can be path planning, anything. So that's how the importance of computer vision comes into play. And computer vision actually is a way of making computer understand the external world. So how it does, it has got a hardware component which is camera, which can be a cell phone, anything, which converts this into a digital form where it can be read by a computer. And there is a CV algorithm, computer vision algorithm, which do the analysis on this digital data and perform the tasks whichever we need. And there are like plenty of applications for computer vision. These are like few of them. It is widely used in the industrial automation. So wherever the visual inspection is there, the computer vision plays a lot of role. It can be in food industry, uh, automotive industry, anything. Sports analytics, you might have seen in football, cricket, anything like there is a ball tracking algorithms, goal line detection algorithms. Even now, uh, players use this sports analytics to analyze the players and whatnot. Like many companies are also investing in analytics these days. Healthcare is another interesting area where the even recent COVID, cancer, what all the areas we have AI working on. Autonomous vehicle, as we discussed, even security for the crowd management, crowd control, crowd counting, all those things, and for satellite imagery to analyze the meteorology, forestry, anything. And there are like, even if you take any computer vision application, there are particular tasks involved, computer vision tasks involved. So these are like main tasks we can see in a computer vision pipeline. One is machine image classification, so which just classify what an image looks like, is it? And object detection. So the detection means like it will give the coordinates, like in X and Y location we have an object. So object recognition will tell what object it is, whether it is a cat, dog, car, or whatever. Like if it is a healthcare, cancer related, it's a abnormal cell, like that. And object tracking, which track the objects along the frames, is basically used in video applications. Image restoration, so nowadays we have seen convert the black and white image to color. And image registrations to do the uh, correction platform. Maybe when we take the photos, it may be not aligned properly, so image registration do the trick. Pose estimation, so this is one example for the pose estimation. So this can be used in sports analytics, like how it is, how people are, any if it is an athlete, how is he running, so how he's tackling, all those things. And for scene recognition, which is widely used in the autonomous vehicle area, and anomaly detection, which anything it can be in a security, like what the anomaly is. Video stabilization is another task. And so once you got to perform these tasks, there should be an algorithm or some logic behind it. So computer vision also has got like traditional CV and deep learning based CV algorithms. So these are like basic pipelines for these type kind of CV algorithms. If you go to traditional CV algorithms, given an input, first it will do the feature engineering. It will like once a feature, relevant feature is extracted, it is passed on to a traditional machine learning model. It can be, and then this output, it depends on the application. If it's a object detection, it will be a bounding box. If it is image classification, it will be like a 1 or 0, like is it belong to that class or not. And in other case, deep learning CV algorithms, an input is fed to a deep learning model and it will give the output. So the main difference between these two, there is no feature engineering step. So that makes our life is simple, like just feed whatever input we are, the deep learning model will take all the job and it's done. So in the other case, traditional CV algorithm, we have got feature engineering and traditional machine learning model. We have to break head on these two aspects. So maybe in the later slides, I will just explain more. And there are like different types of CV algorithms, like whether it is a traditional CV algorithm or a deep learning based CV algorithm. It can be supervised, semi-supervised, or unsupervised algorithms. So what do you mean by supervised algorithm? Because like we need a human intervention to perform the supervised algorithms, to train the supervised algorithms. This what I mean by human intervention, it can be in terms of annotations or label files. So if it is a object detection, then you need to pass image alongside bounding box so that algorithm can learn. And in case of semi-supervised, it's it's like 50% it needs human intervention, and other 50% it can learn on its own. So these are mainly cases for anomaly detections. Like like it's if you take a video like or anomaly in a real world, it's difficult to annotate all kind of anomalies in a real world. So in that case, what we can do, maybe the common anomalies we can label and say algorithm, these are the anomalies I know. Rest, the algorithm can learn like anomaly and a normal way. So then supervised supervised algorithm can learn based on that and perform the task. Other one is unsupervised algorithm where there is no intervention at all. So algorithm is on its own. It has got only the data, no other informations in the form of annotations or labels. So unsupervised algorithm is still like a lot of research is going on because labeling is a very tedious task. If we can remove the labeling from these pipelines, then that will be like a lot of savings. And when we come to traditional CV, as I mentioned, there is a step called feature engineering. So in the feature engineering step, we'll be extracting relevant features. What I mean by features, in case of images, it can be color, histogram, edges, or texture feature. It can be anything. So these features depends on what problem you are solving. So this needs a thorough domain expertise. Then only we can choose what feature is relevant for this particular problem. So that comes with the experience. So traditional CV algorithm will really need an expertise in that field. So this is an example for face detection using a hard-like features. So before this deep learning, the Weiler's algorithm is very famous algorithm for face detection. So earlier it was like a go-to algorithm for detecting faces, eyes, everything. So if you take eyes, and there is a like particular feature is like eye regions are usually darker than the nose bridges, and cheek regions are brighter than the eye regions. So this is kind of a analyzing the contrast. So what they do, like we can do the convolution operations to find this. So if you see here, these are like hard-like features. So the negative, this black indicates negative and the white indicates positive. So if you do the convolution, it will be basically we are finding the difference between those regions. Then these features we can pass to the other ML models and do the face detection. And there are like many machine learning algorithms which are used in the traditional CV. It can be regression, decision trees, support vector machines, clustering algorithms, Bayesian algorithms. But again, we choose which algorithm to go ahead with. That depends on the problem you're working on. So this also comes with the like expertise and your experience. So which algorithm to go with. So I won't be going any details with these algorithms. And so we'll discuss about the pros and cons of traditional ML models. So main pros with the traditional ML models is easy to train and no high computational requirements. It is explainable. Because you know what feature we are using and what algorithm we are using. So we can actually reason like why it is failing, why it is working, and it's easy to deploy because of not much dependencies, all those things. So it's easy to deploy in a real world scenarios or real life problems. And other cons are, as I mentioned, it's need a domain expertise to come up with a feature. Or sometimes a feature working on one problem may not work in another problem. So feature engineering is a very difficult task. And also choosing an algorithm also requires a domain expert. So after the traditional thing, then comes the artificial neural networks. So artificial neural networks has been there in 1980s itself. So this is basically inspired by the biological neurons. So at that time, they were not performing well with the traditional CV algorithm. That because of a lot of reasons, like at that time the computation was not that of a top notch like us now, and also the availability of data is also not data is not rich at that time. So because of those reasons, ANN was not considered as a very superior algorithm. Maybe the traditional CV algorithms were performing better. So this is a typical artificial neural networks. So this is the input layer, and there will be a hidden layers and an output layer. So this input can be the features, and these lines are the weights. And then what will happen is it will just multiply this weight with this input, then will come the output layer. So based on the values at these regions, like that depends on the whether it is an object detection or a regression problem. The output depends on that. So this is the basic idea of neural networks. So these circles are called the neurons. So then comes the deep learning part. So it is a new version. We can tell like a new version of a new artificial neural network with lot of hidden layers. Now earlier neural network layers were limited. That's because of the availability of computation, all those things. Now with this CUDA and all, we can easily scale up the number of layers. So other thing is availability of data. We have like a lot of data available in the net. So this is the one slide I've taken from the Anthony's course. So here it's clearly written why deep learning. So there is it's a graph against amount of data and the performance. So as you see, the older traditional algorithms performance plateau even if the amount of data increases, but the deep learning algorithms still increasing with the amount of data. So CNN or convolution neural network is a kind of it's a deep learning algorithm which got famous with the introduction of AlexNet in 2012 after it winning the ImageNet. So that was like uh, the turning point of the computer vision. From that point onwards, there are like plenty of research work was and lot of convolution network also introduced. And this is the first paper which really did a breakthrough in the computer vision. And this is the architecture of AlexNet. So yeah, you can see like this is the image, and here we'll be doing the convolution, and these all are convolution layers. So in between you can see the max pooling. So max pooling is just take the max of those regions. So and how it is like here it's written like AlexNets, they are like as at that time like there are like CUDA like in this lecture itself you might have heard about the CUDA and how it's the parallel processing. So here the convolution operation is also highly parallelizable operation. So for that reason we can easily uh, distribute this computation to different cores. By that time we can reduce the training time for these algorithms. So that's the like uh, that computation is the major breakthrough that like uh, that made this CNN revolution happen. With the CUDA, with availability of data, like now we have like plenty of image datasets available, like CIFAR, ImageNet, or whatever. And if I dig deep into convolution neural networks, so earlier I was mentioning about the feature engineering, right? Like in the traditional CV algorithms, also like given an input, it will extract the features. It can be edge features, whatever. Then it will feed into a ML model, and finally it will generate the output. So in convolution neural network also, what is happening is like if the first initial layers are as is shown here, it will extract the basic level features like edges, all those things. And in the subsequent layers, it's a feature of the features. So then feature of feature, it can be the texture, all those things. So that's how it is able to classify or perform whatever operations with a high accuracy. So these are like uh, visualization of these neural activations. So there are like a lot of studies going on to how to visualize or make it interpretable how the CNN works. So these are like visualizations for that. So if you go to DistilPub, there is a site there. We can actually see the papers where they have do the mainly focusing on the visualization of these neural networks. And deep learning pros and cons. If you see the pros is best performance measure, and you don't need feature engineering. So for that matter, it's easy to switch. Like if you have like multiple problems to be solved, you can use the same problem, same network for everything. Only thing is you need to retrain it. That's the only thing you need, and you need sufficient data for training. So there is no much of a domain expertise. So suppose you are an engineer and you want to do the cancer detection, you can easily do that. Like you may need an annotation from a experienced doctor. You can just pass it over the network and you can train it. It's done. And for the deep neural networks, it's easily adapted to new problems, as I was mentioning. And other cons are it requires high computation, and most of these deep learning tools also have a lot of dependencies. So when we do the making a deployable code, then that will become a huge task, and it requires huge amount of data. And as I was mentioning, the pros about the traditional CV is explainable, but compared to that, deep reasoning, the output of a deep learning algorithm is very difficult. Like if the algorithm is not working, then it's difficult to come up with a reason because we don't have much theoretical knowledge why deep learning is working. So still an active research. Other thing is hyperparameter tuning. It's like uh, even if you we still say like we don't need feature engineering, but hyperparameter tuning is also very tedious task. Like what batch size, what lane rate, all those things. Nowadays there are like lot of tools that come up with. We can automate those things to some extent. So in that way, this is not a big problem. So other more applications for deep learning. So these are some of the work I have already done and currently doing. So damage inspection is one thing currently I'm working at Picolt. So basically it deals with vehicle and do the damage inspection, like what all kind of damages are currently in that, whether it is a scratch, chip, dent, and what extent it is. And earlier companies I was working, one was pap smear image analysis, like to diagnosis for the cervical cancer. So we were working alongside the Kidway Hospital in Bangalore to collect the data and working with the doctors. And we are also collaborating with IT multiplexers. And other thing I was working dash cam video analysis because these days in Singapore, all those places like for the insurance claim, the dash cam videos are must have. And in now, what is going on? Some person is actually doing videos and saying like what is actually happened. So we were trying to automate like how the crashes happened. Is it the driver's fault or somebody else's fault? Those kind of things. Like basically doing the dash cam video analysis using the AI. So these are the things I have worked on, and this is what I have. So I conclude with that. If you have any questions, so I'm happy to answer.